Bismillahirrahmanirrahim. Today we'll be doing lecture number 7A, control volume form of the conservation law or control volume form of first law of thermodynamics. Last lecture we did set that was the control mass form of conservation law, in which the mass of the system was fixed, in which in other term what we are saying, like there was not mass moving into the system and there was no mass leaving the system. And that's true for many laws, like Newton law and thermodynamic law. But most often, like in a propulsion or power system, for the turbine, for a compressor, for a condenser, we are more interested in control volume form rather than the control mass form of the conservation law. What we are saying, like we are more interested in what actually is moving into the system, what kind of energy is moving into the system, and what kind of energy is moving out of the system. On another term, energy moving into the system with the mass and energy moving out of the system with the mass. So obviously we are more interested in the rate of change of energy due to the mass flow rather than just the fixed mass of the system. So this requires us to use the control volume form of the thermodynamic law, and that's what actually our today topic is. Before we go to the first law of thermodynamics for the control volume form, let's have two of the assumption. One of the assumption is the conservation of the mass, the mass. The For the control volume shown over here, what we are saying, like the mass of the system is conserved. In other term, what do we mean by mass of the system is conserved? What we are saying, like there, when we are saying like mass going into the system and mass leaving out of the system, is actually the rate of change of mass. For a special case, what we call it as the steady flow condition. In a steady flow condition, the mass flow into the system and the mass flow out of the system is equal. What I mean to say, like if I'm saying like 2 kg per second of the mass is moving into the system, and 2 kg and obviously there would be 2 kg per second of the mass leaving out of the system. So the mass of the system is conserved. You can imagine, like in any of the system, like let's say for example, if I'm saying like we are saying like 2 kg of mass is entering the system, and let's suppose 1 kg of the mass is leaving the system. So that would mean like the mass of the system inside the system will be increasing. Or if I say like there is a certain mass inside the system and the mass of the system leaving is greater than the mass which is entering the system, so in other words, what we are saying, like the mass of the system would actually going down. So in our assumption, there is a conservation of the mass. That mean like the mass into the system is equal to the mass out of the system, and that's what we call it as the rate of change of the mass is equal to zero, or there is no change in the rate of the mass. Uh, then we have got the assumption, same assumption, conservation of the energy. That mean like rate of change of energy is rate of change of the energy is fixed. We did said in a last lecture as well, and I did I know with a very simple equation, that was change of energy is equal to heat transfer minus work. That was for the piston and cylinder, if you remember, for the in our last lecture. Yes, we will be doing the same law, but we will be doing in a rate form. So that means rate of change of energy is equal to rate of heat transfer to the system minus rate of doing work. So that means like we are talking about rate of total heat transfer to the system and rate of doing work by the system. So that's what actually our conservation of the energy for the rate equation would be. If we are looking at the system, so in a earlier system, in a fixed mass system, what we were actually supposed to say, like there was no moving of the mass into and there was no moving of the mass out of the system. That's what we are again saying, like the mass was fixed. But for the rate of change of mass, actually, so we are talking about the open system. For the open system, there would be actually mass going into the system and there would be mass leaving the system. And with that mass entering and leaving the system, there would be a pressure P1, let's say P in initial, there would be volume initial, there would be velocity, let's suppose initial, and let's say at the end we would be having pressure final, let's say volume final, and then velocity final as well. So that means like there would be actually the values would be different as initial as state 1, and the value would be different at state 2. So we are talking about the system in which the mass is entering and leaving the system, and with that mass actually obviously there would be energy entering the system and there would be energy leaving the system. The total rate of change of energy of the control volume would be the rate of heat added to the system, control volume, rate of doing work, rate of energy flowing into the system with the mass, what I said earlier, and rate of energy flowing out of the control volume with the mass. So we will be having four different kind of energy. One would be the heat energy, one would be the work energy, one would be energy which would be actually entering the system with the mass, and one would be the energy leaving the system with the mass. So in other words, if I'm combining this one, that would be something like this. So that means like there would be energy, total energy would be heat energy, work energy, and the energy, but we will come back to it later. Now what would be the energy which is entering with the mass itself? Remember, like in our first law of thermodynamics for the control mass system, we did say like the energy which was actually changing was equal to the kinetic energy change, the internal energy change, and the potential energy change. We were ignoring the chemical energy, magnetic energy, and so on and so forth. And yes, for the fixed mass of the system, we did say like the only the control only the internal energy component would be there, and there would be no change in the kinetic energy, and there would be no change in the potential energy, as there was no moving in, no mass moving in and out of the system. But now we cannot assume that the kinetic energy can be fixed, and we cannot assume like the potential energy would be fixed. That means like the velocity which would be entering, at which the mass would be entering, might be different, and the velocity at which the mass is leaving the system might be different as well. It is also possible that the z, if I'm saying like the potential energy, which is z1, it might be different at initial state, and z2, which is actually leaving the system, it might be different at different state, at the state 2. So that means like the total energy now would be actually the energy which is entering and leaving the system now comprise of the internal energy, the kinetic energy, and the potential energy. Make sure that it is actually per unit mass over here. So that's why the mass component, you cannot see the mass component. And also for the velocity, we are actually presenting velocity with the letter C. It is because like for the letter V, we conserve letter V for the volume over here in our thermodynamics, and the height is actually represented by letter Z. For H height, if you been previously using height H, and now H is used for the enthalpy in our thermodynamics. So that's why we are using the C for the velocity and Z for the height over here. So that's the point is actually again. So if I'm talking about the energy which is leaving, entering and leaving the system, we will be having three component of that energy. One would be the internal energy, one would be the kinetic energy, and one would be the potential energy. Again, I'm saying like we are ignoring the chemical energy and we are ignoring any other kind of energy which is not so important for us. So, and yes, let's say in our last lecture, we also defined one of the other energy, and that energy was actually, or other work, if I'm saying like, to be very simple, uh, that was actually, we call it as a flow work. And that flow work was actually when actually we have got a pressure initially, and that pressure is moving some volume inside the cylinder, and the pressure which is at final, and it is actually moving the volume at final to out of the system. So that means like this pressure and this volume is responsible for the work done, and that work done was actually, we call it as a flow work. So remember from a previous lecture, our work done, change of work done was equal to P2 V2 minus P1 V1. If you are talking about the mass, multiply with the mass. And if you are assuming like the mass into the system and leaving the system are different, so you can multiply mass M2 over here and multiply mass M1 over here. So that would be different mass into the system and different mass out of the system. Yes, if we are not talking about the steady flow, but let's say we are still conserve ourselves to the steady flow energy equation. So again, connecting all the energies back, we would be having the heat energy, we would be having the work energy, we would be having energy which would be flowing into the system with the mass, and we would be having the energy which is flowing out of the system with the mass. So our equation, the above equation, would be rate of change of energy, sorry for that, rate of change of energy would be equal to rate of the total heat transfer, the total work done, sorry for that, total work done, and let me do it again. So total heat transfer, the work done, and energy flowing into and out of the system. So that's what actually we call it as a summation sign over here. Um, Again, note that there is no negative and positive sign with the work done. So you can imagine like we can ignore the negative sign when we are writing down the summation sign somewhere written down there. So there is no negative sign because of this summation point. It will be eventually there if we are removing the summation sign from here. So let's say again we are saying like there would be heat transfer to the system, there would be work done to the system, and there would be actually the energy which is flowing into the system and out of the system with the mass. Please note that there would be different kind of a work done for a complex system. We can actually say like for a complex system, we would be having a flow work, we would be having a surface work, boundary work, we would be having piston work, we would be having shaft work, and so on and so forth. So yes, you can actually imagine like there would be different work done over here. So we would be having a shaft work, we would be having a shear work, we would be having a piston work, we would be having a flow work. So we are talking about a complex system in which there are different kind of a work done. We are talking about the internal energy change with the mass, then we are talking about the kinetic energy, then we are talking about the potential energy. Again, assume like make sure like the mass is actually multiplied, this mass is multiplied, and we are assuming like mass in and out of the system is actually same, so that's why m is actually over there as a single m. In a many in many situation, if I'm saying like okay, let's sorry move to one initial one point, and then we'll be moving to this point back there. In our case, let's say if you remember from the above this equation, flow work was equal to change in PV, or if I'm saying like change in a flow work was equal to change in PV actually. So that was actually something like this. So if I'm saying like PV plus U, if you can remember that one. So PV plus U, from the previous lecture when we were doing the enthalpy. So we did said like whenever you are finding flow work and you find internal energy together, you can bracket them both and rename it as enthalpy. So what point is over here, if you find the flow work in here and you find the internal energy in here, you just bracket them and make sure they are actually represented as enthalpy now. So yes, the flow work and internal energy would be enthalpy now. So just moving over here, so the flow energy and the internal energy is enthalpy now. So our equation is reduced somewhere here now. In most of the application in this course actually, uh, we would be not much looking at the shear work. We would be not looking at much of the piston work. Even if there is a piston work involved, that piston is actually, we would be taking the work out of the piston using a shaft or something like this. So we would be talking about the shaft work again. So in most of our cases, we would be ignoring the shear work, we would be ignoring the piston work. So we are only and only left with the shaft work over here. So there would be now the above equation would be heat transfer, shaft work, and the energy which is actually going into and out of the system with the mass flow rate. Again, make sure that U plus PV was equal to H over here. Removing the summation sign, so you can have the heat transfer, sorry, that is rate of change of heat transfer, so Q dot would be there. Heat transfer to the control volume minus work done plus energy going into the system minus energy leaving out of the system. So the rate of change of energy would be heat transfer into the system, work done by the system, energy flowing into the system, energy with the mass I'm saying, and energy flowing out of the system. So for our special case, we did say like there would be rate of change of energy transfer, or in other words, there was a conservation of mass and there was a conservation of energy as well. So we were talking about the steady flow equation in which the rate of change was equal to 0 or 10 to 0, we are saying like, and in that case mass into the system was equal to mass out of the system, and that was equal to rate of change of mass. So in a special case of the steady flow, which is actually explained now, rate of change is equal to 0 or 10 to 0, mass in and out of the system is 0, mass in and out is equal to mass rate. So the above equation, which is over here, would be rearranged as heat transfer minus work done, as this point d by dt would equal to 0. So that means like this side would be equal to 0. So heat transfer minus work done would be equal to mass leaving the system minus mass entering the system. Make sure the sign is changed when you are shifting this thing from here over here. So that means like we are talking about the this equation, which is actually Q minus W would be equal to energy in leaving the system minus energy entering the system. Also note that m dot is over here now. We have removed this mass now. Mi is equal to me, and that is equal to m dot. So we are talking about only one m dot. This kind of an equation, which actually we have just derived, is actually for a special condition, and that special condition is actually we call it as a steady flow. This is our energy equation. So this whole equation can be called as the steady flow energy equation. This is actually our first law of equation. You can call it as a first law energy equation as well. This is actually our first law conservation, first law for the control volume. So this energy equation is actually can be called as the steady flow energy equation for the control volume form of the first law. So this is the first law of thermodynamics, and make sure again a special case when d by dt is equal to 0 and mass in and out of the system is equal to m dot. when, yes, when there is no in and out is not equal, you can actually replace by its original mass. When there is no rate of the, when there is no steady flow, you can actually change in different way. But yes, we in our course we will be looking at a very simple condition now.